Alright, so welcome to another set of notes, video, me talking, you listening, so on and so forth. We're going to go over exponential functions, for those of you that were not able to hear the lecture before. So here we go. Today what I hope you would do after you've seen this is that you'll understand and describe characteristics of exponential functions. So moving on, what is an exponential function? It is a function that is written in the form of a times b raised to the x power. A cannot equal 0, b cannot equal 1, and b must be greater than 0. So we're going to see some examples here of what we're defining as an exponential function, and realize that you're getting a basic introduction to this. I might go further than what this is here, but the main focus for STAR, I'm going to presume, is dealing with just the a and the b. So what does the parent function look like? Parent function looks like f raised to 2 of the x power. So if you were to look at that one, you would see it look something like this. And if you notice here, there's a table that I'm making that has these numbers, 4 raised to the 16. So that's saying 2 to the 4th is 16, 2 to the 3rd is 8, 2 to the squared. But notice here, like the negatives, positives, and negatives are kind of reciprocals of each other. So even as positive 3 and negative 3 are inverses, so is 8 and 1/8. One is like an additive inverse, where the other one's a multiplicative inverse. Because again, negative exponents give you like that reciprocal. Also, there is a boundary that, say, exponential functions approach. That's called an asymptote. More specifically, is a horizontal asymptote, because there are vertical and diagonal asymptotes, but in Algebra 1, all you're going to see is this one, the horizontal. And it will always be y equals some number. Should be, in most cases, y equals 0. At least as far as what we're going to see in this class. Alright, so we've got 2 to the x. Let's look at what these graphs would look like. 2 to the x, 3 to the x, and 5 to the x. Okay, so this is not the best picture, but you can kind of see the graphs there. In blue, you've got the parent function. In red, you've got 3 to the x power. And in black, you've got the 5 to the x power. And basically, as you see, as the numbers are getting larger, the lines are going up. But notice they're still going through the same y-intercept, and they're still approaching 0. So they're still going through 1, but they're still approaching 0. So this really technically should be considered more of a what is called a horizontal compression, but I don't think we'll have to worry about that. So we're going to say right here, this is a vertical compression, or stretch, I'm sorry. As the b is getting larger, this is going more up, faster up. Because if you also look closely at the graph, this is what's called exponential growth. This little section also shows that the 5 to the x was getting to the 0 quicker than, say, 2 to the x. So kind of see that there. So do notice that they would go up quicker as the lines get, or the numbers get bigger. So now let's look at 2 to the x, 1/2 to the x, and 1/3 to the x. Okay, so as funny as it is to say this, but my calculator is dying, so this will be probably the last picture I can put up for now. I apparently need to charge up my calculator. But you can see here 2 to the x is the parent function, but the 1/3 and 1/2, yeah, they actually go down. So they actually kind of do a reflection over the y-axis, which would be considered, well, that's about it. It's just a reflection. But again, notice how these two are opposites of each other also. So these graphs cause it to go down, which would be a reflection, which we would call an exponential decay. So kind of keep in mind that you should know what's the difference between an exponential growth and an exponential decay. So what is that? Well, when b is greater than 1, there's a growth. When it's less than, or I'm sorry, between 0 and 1, there's a decay. So some fractions maybe. Anyways, here we go. Next part. I am literally squeezing whatever juice I can get out of my calculator. But anyways, okay, 2 to the x is this one right here. And then you've got 3 to the x, which is this one right here, and 1/3 to the x, which is right here. Notice that they're all still approaching 0, but now we can also tell that in a more true of a stretch and compression, this one's making this one go up higher and also crossing at the 3, so it's kind of changing the y-intercept. and this one is going a little bit lower, and again also crossing at 1/3. So again, changing the y-intercept. So there you can kind of see that that's more of a true vertical stretch, and a true, because we always said the number in the very front would tell us about vertical stretch or compression. And then we can see here those will also affect the y-intercept. All right, and go with the idea that that one could have been 1 times 2 to the x. So that would help that. Oops. Okay, so let's look at the next part. What happens if I add or subtract? And I just want y'all to see this. But basically that would move it up or down. So that would be considered a vertical stretch, vertical shift. And it would also change your asymptotes, and those could become like the asymptote numbers based on that. So there I'm saying, like in the parent function, y is greater than 0, the asymptote is y equals 0. Then in this one, y would equal 1, and this one, y would equal -1. And that would also change your range and domain. So let's look at that idea. And we're going to skip that part. Actually, I'm going to leave that going because I thought about this. These will be the horizontal shifts, the ones that move them left or right. I am mainly asking this of my pre-AP classes, so if you're in my CEP classes, you don't need to worry about that. But those would move it to the left and to the right. It may not look like it, but it does. If you were looking at the table, you would see how they literally move them one spot over or one spot to the left. But kind of can't judge that based on the graph, so you have to be careful with that. All right, so let's look at this last idea, or this idea here. 2 to the x is the parent function. We now know the y-intercept is at 1. The asymptote is at y equals 0. And then the domain would be all real numbers, and the range, well, the nice part about the range is if you know your asymptote, then you should know your range, because take the asymptote, there's your range, but instead of being equals to, it will be greater than. So very simple, just like that. So if I wanted to do, like, say, a rough graph, and say I had something like y is less than, that was off. Let's try that again. F of x is equal to 1/4 raised to the x power. Then I would know that's still crossing at 1. So the y-intercept will still be at 1 because there's no change in my y-intercept there. It's going to be the asymptote Did I spell that right? I don't remember. Hold up. It's 1S. Let's try that again. Okay, the asymptote would be y is still equal to 0. So then I would have a graph that I know would look like it's kind of steep going this way, but would go like this. So approximately something like that. Now if I generate a table, I could easily see how that would work. But the domain here is still going to be all real numbers. There should be no limit to that. And the range should be easy to say, okay, look, here's my y. The asymptote was y equals 0. Then the range has to be y greater than 0. And since all these lines should be going, say, above the y-axis, they should all be greater than. Since b is going to be less than. Now, if I put an a where a is negative, then that would flip it over. It is possible to do it like that, but I probably won't be that cruel. Anyways, that should cover pretty much everything. You already know how to, say, tell if they are exponential just by looking at a table and dividing. Remember, divide and look for a common ratio. So that should cover pretty much everything that we're covering with this section. And if you do have any questions, feel free to ask in class. Thank you very much.